Okay, here's another interesting calorimetry question, actually an old IB question from back in the 90s. This time though, instead of being given an initial and a final temperature, you're given a graph with temperatures that have been monitored during the course of a chemical reaction. So we're going to have to estimate temperature change here in due course. Well, the reaction we can see is between zinc and copper 2 sulfate, and the first thing we're asked to do is to write a chemical equation for the reaction. So zinc and copper sulfate undergo a redox reaction or a metal displacement reaction in which the copper is displaced by the more reactive zinc to form that, and we can see straight away that that balances nicely. So we've got a 1-to-1 ratio of the reactants. We need to know that 1-to-1 ratio because next it wants us to find out which of those two reagents are just reactants, which of them is in excess. Well, the zinc is given as a mass of a powder, so to find the moles of zinc we just use mass over molar mass, which is 1.2, and if you check your periodic table you'll find the relative atomic mass of zinc is 65.38, which gives us an approximate number of moles. I'm just giving 2 sig figs, 0.018 moles. The number of moles of copper sulfate, well, the copper sulfate is a solution, and we've got its volume and we've got its concentration. So if we know concentration and volume, we can find the number of moles. Can convert those cc's to dm cubed by dividing by 1000, and I end up with 0.005 moles, which is a lot less than 0.018. So we can tell then, excuse me for moving over here, that the zinc is in excess. The copper sulfate is limiting. So it's the limiting reagent we'll be using later on to help us figure out how many moles, how many joules per mole are produced. Okay. Moving on, here's the rest of the question. It tells us that the highest point in the graph is at A here, highest temperature is that point there, and they want us to know what's happening in the system at that point. Well, the reaction's obviously over, and the energy that's been released, or is still being released perhaps, must at that point be equal to the energy that's being absorbed from the surroundings. So I think we can say here that heat evolved from the reaction at that point must be equal to the heat being absorbed from surroundings. After that point, the heat absorbed from the surroundings is greater than the heat evolved from the reaction, and so the temperature will gradually reach room temperature. Okay, well this time we have to use a ruler to draw a suitable line on the graph that's going to help us estimate what the rise in temperature would have been if the reaction had taken place spontaneously. Spontaneously, in other words, if the reaction had taken place straight away, immediately, then at this point, this is when the reactants were mixed at 2 minutes, if everything had reacted and no heat had been lost to the surroundings, the maximum temperature change should have occurred there. But it didn't. You can see from the points on the graph that the temperature increase gradually to a maximum. That's because the particles of the zinc are not able to react with the copper sulfate all in one go, and we've got heat being lost to the surroundings. So if we take a ruler, we should be able to draw some lines on here. Could draw a line here, and then if we take our ruler up, we want to try and get a best fit line I'm not very good at using this ruler to draw a best fit line. That's ish. Okay, I'm going to use that to draw my best fit line all the way up here, and then I can see that this, at this point here, this temperature change should move across to my axes at that point there. Oop, I've missed it slightly, haven't I? That line should really be just here at that point, and it should have moved across to the axis to give me my maximum temperature that I should have had if everything had reacted spontaneously. Well, that means that this is my temperature change, my estimated temperature change, and from the graph I've got, it seems that delta T is approximately, I'm going to say 26.8 subtract 17 excuse me, I got lost then. That gives me about 9.8 degrees centigrade. So, calculating how much heat was evolved during the reaction, well, Q equals the mass of the solution. Well, the mass was 25.0 cc's. Because in this reaction we had a solid reacting with a solution to produce another solid and another solution, the temperature we recorded really was only of the copper sulfate solution, because the solid was a solid, it hadn't dissolved. So when we include the mass here, we're going to use the mass of the copper sulfate solution, and we are not going to include the mass of the zinc. So I now have 25 multiplied by 4.18 multiplied by the temperature change 9.8 gives me about 1024 joules. Now here, please remember that I've made a couple of fairly sizable assumptions here. I've assumed that this mass here, this volume of copper sulfate has got the same density of water, so I've used the fact that 25.0 cc's of water has a mass of 25.0 grams. That's an assumption because it's not pure water. I've also made an assumption here that the specific heat capacity of the mixture is the same as that of water, 4.18. Of course it's not. The mixture had some metal in it, which was probably absorbing water. There was a thermometer in it, probably, sorry, not absorbing water, more absorbing heat. So we've got some big assumptions made here about density and specific heat capacity. Oh, this says 3 sig figs. So back here, 1020 joules. Okay, so that's the amount of energy that was evolved for the reaction we studied, just using the mass of zinc and the volume given. But now they want the enthalpy change of reaction in kilojoules per mole. So if we take delta H being equal to, the temperature's increased, of course, which is evident from the graph, so we know it's an exothermic reaction. We know that the energy evolved was 1020 joules, and going way back to the start, if you remember, it was the copper sulfate that was limiting, and there was 0.005 moles of the copper sulfate, so that's what we should be dividing here. Oops, 0.005. And so if we divide out here, we end up with approximately, I'm rounding, 2,000, sorry, I've forgotten to round, I'll round here when and I'm dividing by 1,000 to convert to kilojoules per mole. So I've given 3 sig figs and I've rounded up. Actually though, if we really think about the question, if we go back to the temperature change we used, that only had 2 sig figs. So strictly speaking, we might only want to give this value as minus 200 kilojoules per mole. The accepted value for the enthalpy change is negative 218 kilojoules per mole. Determine the percentage error. Well, the percentage error, we take the actual value, negative 218, we subtract from that our value, the experimental value, let's say negative 200, and divide that by the actual value and multiply by 100. That's our experimental error. So we've got 218 subtract 200 divided by 218 multiplied by 100, and we get about 8%. And I'm just leaving one significant figure because I shouldn't be giving decimal places, because the values I've given here and here don't have any decimal places. So we can only stick to the same number of decimal places that they have, none, because we're adding or subtracting. Okay, now suggest reasons, it says 2 reasons, why there's a disagreement between the experimental value and the accepted value. And there's all kinds of things. Of course, the major reason, the major error, is the heat lost to the surroundings. But there's also assumptions that the mixture had the same density and heat capacity as water. So there's another 2 assumptions. Also, we also assumed that the zinc metal and the copper metal had 0 heat capacity. We also assumed that the thermometer had a 0 heat capacity. So lots of things to evaluate there. Okay, I hope that's helped. Thank you very much.